Hello and welcome to this series on in-vehicle networking. Everything vehicle networks in terms of CAN, LIN, what it means out of the box, this kind of thing. But joining me to take us on this journey, I'm delighted to say, is Andy Crook. Welcome, Andy.
Thank you very much, Steve. Pleasure to be here.
So we've created a series of videos that will take you from network terminology through to network measurements, and then we'll actually move on to each bus, each network and topology independently. So we'll look at LIN bus and CAN bus. We'll move on to video 5 here, which is FlexRay. Video 6 will take us to CENT, and then finally video 7 is 10 base T1S, which is actually Automotive Ethernet. Let's just go through what the actual brief is here, and that is helping to remove and break down the fear factor, because there's this issue surrounding networks. Vehicle comes in, multiple network codes, where do you start? So much help is at hand. PicoScope at the core of that. Something you suggested, Andy, and that was, first of all, demystifying networks, because there's so much jargon around terminology that's necessary but sort of doesn't lend itself to automotive.
Yeah.
And I think if we can crack through and just break down what these terms mean, all of a sudden the penny drops. You're able to assemble a network almost in your head. We'll move on to network measurements. So that's how we apply PicoScope. We'll also have a look at several, I don't want to say common faults, but certainly faults that you will tackle, those that certainly appear with networks. And then we'll break each one down into the style of bus. So when I say the style of network, so here we've got LIN bus, and CAN bus. Those probably are the main two, I think. Then we'll sort of look at FlexRay, which has been around for longer than you think, and perhaps the fact that we haven't, or I personally haven't seen many problems with it, is testament to how reliable it is. We move on to something called CENT, single edge nibble transmission. There's a group of terms that you put those together, it doesn't really mean a lot, but it will, I promise. And then finally we'll have a look, I was going to say into the future, but it's not, it's actually here. That's 10 base, this is Automotive Ethernet. So I think when we get to that point, in fact that is so new that we don't have a vehicle with that network on there, but we do have models, so we can do a sort of a benchtop simulation. So on that, let's go on with video 1. So in this video, Andy and I explain the meaning behind the terminology used in vehicle networking, which helps when we apply PicoScope and commence diagnosis. So let's break down the terminology of vehicle networking. So I think you mentioned this, Andy. When we started on this journey, Andy sort of just put the brakes on immediately and said, so how are we going to start? We need to go right back to the beginning. What is a network? What does it do? So here we are. It's a network. Automotive is a group of computers, ECUs, modules or nodes. Nodes is a term that you mentioned, Andy, we should be getting to grips with that term.
Yeah, so although we probably think of these things as ECUs, or maybe we use the term modules, because when we think ECU we think a box with loads of wires coming out of it. But they're not necessarily that, as we'll see as we progress through the videos. So the correct term in network terminology is a node. And it's not, obviously nobody's going to come and penalise you for using any other word.
Yeah.
It's not going to affect how you go about your diagnosis, but it's possibly better when we start to use terminology correctly, or more correctly, when we want to identify something, so everybody understands what we're talking about when we're using the right terms. And I think it just comes down to that, Steve, more than anything else, is when we start understanding this technology a little bit better, we start to use the terminology more, and we just become more and more familiar with it. So we just need to get to grips with it. We can't hide away from it.
No.
So you've just got to grab then it'll buy the phones and give it a go.
Yeah, you're right in terms of all the study that's gone into looking at these or creating these videos. The term node comes up time and time again. So for us, ECUs in automotive or modules, but nodes is the correct terminology. Anyway, they are connected together either by a single or multiple cables known as transmission media, or we know it as the data bus or even the bus. But yeah, that term will also come up, media, because a data bus is not necessarily a cable pair, otherwise it could be over the air. Network impedance, this is something that we'll look at in several up and coming videos, but it's an important one. It's a resistive measurement, so the unit is ohms, of the data bus circuit, and it is chosen specifically to prevent signal degradation, minimize errors and latency in communication. And network impedance can be configured using termination resistors. So you may have, with your diagnosis in the past, carried out that fundamental check, and it will reveal several faults straight away, and that is network impedance, just the resistance of the network. I've just included here the maths behind it, but there is a little tip here that whenever you get resistors in parallel, like we have in a CAN bus, when they are the same value, so here they are 120 ohms each, you simply halve them. So the total impedance of this circuit is 60 ohms.
So before so go back to that. So you'll often hear me when I talk about doing basic electrical fault finding, that resistance is futile. However, in networking, and especially in CAN networks, resistance is a key measurement. And when we start looking at the various techniques and measurement techniques we can employ when we look at networks, resistance is a fundamental measurement. So although if you're an experienced fault finder, you're probably thinking, why don't we do a volt drop test? It'll all become clear if you're not used to testing networks, why testing network impedance is so important.
Cheers, Andy, thank you. So what is network topology? This comes up again and again when you're actually looking at the circuit and understanding how it's configured from the topology diagram. If they're lucky enough, the vehicle manufacturer's lucky enough to present you with one, gives you a clue certainly as to who's online and what order to perhaps diagnose in. But what it does, it describes the physical construction of ECUs in a network. Now there's several ones here, point-to-point, bus, ring, star, etc. In my experience, it tends to be bus topology, ring and line, perhaps star as well. Yourself, Andy?
Yeah, definitely star.
Yeah.
As well as ring and bus, as it's called there.
Yeah.
The key thing to understand is when you're doing a diagnosis, a network diagnosis, you need to do some form of just-in-time learning on the system that you're looking at. Because if you don't understand how the network is configured, that's basically what topology is. It's how is this organized? How are the modules or nodes connected on that bus?
Yeah.
Unless you know that, you could make fundamental mistakes in your diagnosis. So although you can dive in and start taking measurements, if you have a fault on that particular network and understanding the topology.
You got that as well? Topology.
I can't say that.
That's all right.
Understanding the topology will help you with your diagnosis, because depending on the type of network will depend on the fault and how it appears with the measurement.
Yeah. On that, I think, why do we have so many topologies? And the brief explanation is it depends on what the vehicle manufacturer wants from that network. So performance is critical, of course. Cost is always comes into play, cost. So the type of network they're going to use for a certain system, the performance that you get from the various topologies, reliability. So think about brakes in networks, an open circuit, something like that. Can it still function? Scalability, can we add to what we've already put on, so accessories and such. Complexity, On some vehicles, not so important. On others, unnecessary complexity is wasted money, wasted effort. And another one's security as well. Okay, so a gateway, this is something we'll hear time and time again. A gateway is typically an ECU that allows the exchange of data between networks using different languages. And I've actually put languages as protocols there. We'll come to protocols a bit later, but an example here is CAN ECU talking to a LIN network, so they're exchanging data, information, but they must go via the gateway because they speak different languages.
Yeah, simply put, a gateway is a translator. It allows two different networks to talk to each other through an intermediate. So a bit like a translator. If you were speaking to someone who spoke a different language, that's effectively the function of the gateway in a network.
And on the languages, what is a protocol? A set of rules that govern the style of communication to be used between ECUs. For ECUs to communicate with each other, they must speak the same language. Now, you'll see, to me, it's opened my eyes working with different networks, just how many different options and permutations there are of exchanging a 1 and a 0. It's, I'm not sure sometimes whether it's necessary, but we've got them, we need to work with them.
So protocols you can think of as the rules of the language.
Yes, yeah.
So if different languages arrange their words in different orders,
Yeah.
And it's the same for networks. So when a protocol is established, it's just an agreement of how a particular network will communicate, and that includes the language and everything that goes on with that. So it can be, as you say, it's the options here are almost infinite, even though we're only talking about a 1 or a 0 in most cases.
It's probably worth mentioning on that whilst we've set out here to describe every protocol, by no means are they definitive and exhaustive, because again, we will place further information about these protocols on the Auto forum, so we can perhaps allow you to dig deeper, but the more you research, the more you'll find.
Yeah, it's never ending.
It's never ending, it is, yeah. A term that comes up, multiplexing, so a method to combine multiple messages into a single message. That's called muxing, which is then transmitted over the network and split back into multiple messages, so demuxing. So here, if we think of the ECU1 that has all these inputs, we could actually connect temperature to temperature by a wire. So here then we'd have 1, 2, 3, 4, 5, 6 wires moving across from one ECU to another, or we can get all that information over through encoding over a piece of wire, or it could be over the air, the transmission media or the bus, single wire over to another ECU that can decode, demux, and obtain the same amount of data. And the benefits, they speak for themselves there. Efficient use of bandwidth we'll come on to. Reduction in wire count, there's the obvious one, and harness weight. Inherent reliability, arguable, but you know, they are generally reliable. Fewer components and connections, that's got to improve reliability. Reduce cost, that comes with reduced weight, doesn't it there? And a good one here, incorporates diagnostics. So as you'll know, we can connect and communicate on a digital level and obtain data about any one of those inputs, temperature, RPM, miles per hour, whatever it may be. So that brings us on to the bus and what is a single wire and a differential bus. Well, a single wire transfers signal over a single wire, single cable, where the voltage levels are measured with reference to ground to convey the transmitted data. So if we just stop there for a second and think of LIN bus, this is the example on the left. We've got a 0 volt to 12 volt signal with reference to ground, where anything at the low level, 0 volt, represents a 0, a logic 0. Anything at the high level, a 1, logic 1. Conversely then, a differential bus transfers signals over a twisted pair of wires, where the voltage difference between the two wires conveys the transmitted data. So on the right hand side we've got CAN bus, Differential, so you've got can high and can low, and when we subtract one from the other, we end up with what we call the differential voltage, and that is exactly what the computer is looking at to convert, to decode into the ones and zeros as required. I have put some additional data in here. You'll see 3 lines of decoded data. We've got a line of binary, which we'll come to, a line of decimal, and a line of hex. So PicoScope can do all this for you. I've also added a couple of additional measurements called top and base. What are they? Well, you'll see there that the voltage rises up to, well, we'll start with the left. Why don't we just go with the left side, 0 to 12 volts. Quite often on networks you will see something called ringing. That's quite normal. Sometimes we don't want to measure that peak, we just want the sort of base, so we want to exclude the overshoot and the undershoot. So we ask for the top measurement, which is pretty much the average top value, and equally the same for the base. And there we can see on the left our top value is 12.3 and our base value is 1.087 volts, so not quite ground. Similar on A minus B, this is the differential on the right hand side. We've got a top measurement of 2 volts and a bottom measurement of almost 0 volts. So yeah, sorry.
So I think it's key to point out at this stage, Steve, that why you would have a differential bus and a single wire. So obviously when they decide the protocols, the manufacturers, they want to make things as cheaply as possible. So in non-safety critical systems, you can get away with using a single wire, because if that function fails, for most things on a single wire network, there'll be some form of redundancy. It could be manual redundancy. So if you think about automatic lights, the driver can still have the option to turn the lights on themselves. So it's not safety critical, and that's a feature where you'll see a single wire network. Whereas on a differential bus where we have 2 wires, the reason for having 2 wires is safety. It will be very, very fault tolerant. So if you lose 1 wire, so if you've got a single wire bus, you're going to lose all of that communication. With a differential bus or twisted pair or 2 wire bus, that isn't always the case. You can have faults on the network and the network will still work. So that obviously, if you just look at it in simple, the number of wires terms, makes it nearly twice as expensive.
Yeah.
But you also have to have
exactly, yeah.
2 transmitters and receivers, so the computer becomes more expensive. So you can see that where it's not necessary to have all of that redundancy and fault tolerance, you can use a single wire bus. And that's well worth mentioning at this early stage, because otherwise you'd be thinking, well, why don't they just use a single wire bus all the time? Or why don't they use 2 wires or a differential bus or what's commonly known as a twisted pair? And even the act of twisting the pair makes it more fault tolerant. So.
Yeah, no, thank you, Andy, you're right. And you mentioned something there about fault tolerant, that we can still have communication when certain events happen. We will come to that during the CAN diagnosis practicals. You'll see there that there's actually several faults they can introduce and we've still got communication. Okay, so what is encoding and decoding? So encoding is the process of converting values into secure data for transmission and storage. And decoding is the process of reconverting encoded data, into the original values. And I like this model here because this is what we do day in, day out, is encoding and decoding. So if I was to use the example where I have a written word, I encode the letters in those words into sound. I transmit those sounds over the air. That's the transmission media. It could be a piece of wire, but how we communicate over the air. The receiver will receive those sounds, decode those sounds into letters to enable him, her to write the word. So there we have basically communication, a network, encoder, which then transmits the media between the two, the receiver, decoder.
And just to add just the final bit to that, that's not on the screen, but the final bit of any communication is to find out whether or not it was successful. Was the message received and understood?
Understood, yeah.
Which is the final bit, which is why you would possibly, as Steve said, you would get the receiver to write down the word, and then the encoder could see if the word had been written down correctly. And that's when you know effective communication has taken place.
You're absolutely right, actually, yeah. I can transmit all day long, whether you've understood or got it correct, and vice versa. Yeah. Just nod. Just keep nodding. All right, what is a transceiver? Another term. So inside each ECU node is a transceiver designed to transmit signals onto the bus. And that's generally driving the voltage high or low. And it's instructed by the microcontroller. So all we know of this is what we call the computer, the module, the node. In addition, a transceiver can receive signals from the bus. So not only is it transmitting, it's receiving, it's listening as well, and then relay them, or those messages, back to the microcontroller. Communication between ECU is established by driving the bus voltage high or low. We need a change of state from one position to another and decide in the protocol what state is a 0, what state is a 1. Depending on the protocol, a high bus voltage may represent binary 1, logic 1, and a low bus voltage, binary 0 or logic 0. So a group of 1s or 0s is represented by the length of time the voltage is high or low. So let's just think about that for a second. Not only do we have a change of state representing a high and a low, if we are high for a certain amount of time, that may be a group of 1s. So now we're getting more messaging across, all in a single pulse. I just wanted to quickly explain this transceiver here. If we look at the transceiver, we've got that we are biased to, on this diagram, this is 12 volts. So this is a pull-up resistor. So when this transistor here is not switched on, our bus voltage will be high at 12 volts. When the transistor goes from off to on, we'll go from 12 volt down to 0 volt. And then this will continue, highs, lows, for certain periods to generate the message that wants to be transmitted.
Just to make that clear, Steve.
Yeah.
This is a bit like when you test the output going to any kind of load on a vehicle. So if this was going to a bulb, before the circuit was completed, both sides of that bulb you would have the supply voltage. Mm-hmm. It's only when you provide a ground path, which is the job of the microcontroller, will the voltage be used up in the load, and then you'll get your 0 or low voltage reference. So it's exactly the same as doing a volt drop test on any particular component. Mm-hmm. It's just that we're going to be measuring after the load. Until the load is grounded, which is the pull-up resistor, you will have 12 volts if it's configured this way. And when it's grounded, it goes down to the lower voltage.
Yeah, thank you. Okay, so here we are. Bits, nibbles, bytes and binary. Nobody tells you this at automotive college, do they, that this is where you're going to be heading. But if you get your head into this, it really is, it's good stuff. Or maybe that's just me. Yeah, but I like MBH, so something's not quite right there, is it?
It's called weirdo.
Yeah, thank you for that. But yeah, I'll take that. Bits, nibbles and bytes represent groups of binary data. Just think 0 or 1, which form the vocabulary of computer language to enable communication via the specified protocol. Again, it amazes me what we can do with a 0 and a 1, and how we shift the orders and what have you. So computers, remember this, can only process data in binary format. Ultimately, what needs to be transmitted is this binary data. Some terminology that hopefully will help. A group of 8 bits is called a byte, and it's the main unit of measurement in all computing. E.g., I've organised 8 binary bits there to form the byte. A group of 4 bits is called a nibble, and nibble will become important when we look at cent. There's a clue in there as to what N stands for in cent. A bit, binary, 0 or 1, is the smallest unit of data that a computer can process and store. So there's a little model on the left-hand side there of our bits, how they're formed to make nibbles, and ultimately how 2 nibbles make a byte. I've included the binary number, and I've also included what that means in decimal and how we made up that. So that was simply by adding together the fact that a 1 sits underneath 128. We add that to 64. There is a 1 under 16, so we include that in our calculation, and there is a 1 under the decimal 1. You add those together, that binary number there is equal to a decimal value of 209. So from binary then to hexadecimal, and why do we use it? It's a user-friendly format and it's adopted by humans to represent binary numbers. And the bottom line here is imagine trying to read a huge binary number. It's just ones and zeros. It is very easy to get lost in all of that. So we use a different format to represent that. And when you start working with decoders, you will see that hex just works well. It's easier to read. You have to get your head around the counting process, but I'll just go through it quickly here. So hexadecimal utilises numbers 0 to 9, but then rather than going to 10, we use letters A to F thereafter to represent binary numbers. It simplifies interpretation of large numbers into a compact form. To convert binary, hexadecimal or decimal numbers, use the Windows calculator. It's a lifesaver, this is, and I've got an image of it on the right hand side. It's part of the Windows operating system. Just open the calculator up and click on Programmer, and then you can enter your number in whatever form you like. So if it's a row of binaries, which if you type that right first time, I'll eat my hat because it is binary. Type in your decimal or your hex, whatever it is, and it will spit out whatever formula you want, whatever format you want. Just on the left there, we've got a chart, conversion from decimal to hex, and then from hex across to binary. I've shown here a PicoScope decode where you just see a voltage transition, so where we've got a 0 and a row of 1s, but also what that looks like in hex format, and then what it looks like in decimal. But yeah, remember the Windows calculator.
Absolutely. The only person who can speak all of those languages is Data from Star Trek. So don't worry if you're not familiar with these. Yeah, you're not expected to. That's why there are useful tools available to you. And the decoding function within the Pico software allows you to convert the message into something that you still don't understand, but makes the message more readable. Mm-hmm. And we'll get into that when we do the test and measurement. But if you do want to convert from one to another, as Steve said, the calculator that's built into a Windows program, the operating system, is very, very useful, as long as you remember to select the programmer.
Yes, yeah, which is why I've highlighted it there, because
well done, Steve.
On it, hopefully. All right. So on that, what is a Pico network decoder? Well, the Pico network decoder captures raw signals from the data bus using PicoScope. So this is a physical voltage measurement. We're going to connect to the data bus and just, for want of a better description, sniff the activity that's going on in that cable. And then we can apply a decoder. So once we've identified, and you mentioned this, we'll come to this, but it hadn't occurred to me. I just assumed that we know what we're connecting to, and we don't. We need to establish, have I got the right wire, and have I got the right network, more importantly. The rules of the protocol. So whatever those rules are, we open up the PicoScope decoder and select whatever network it is we're working on. That will convert the voltage levels into binary, hex or decimal, whichever you prefer. And whilst decimal gives you that comfortable feeling because you know what decimal is, you'll soon realise that when you're sort of using technical literature, that everything in my experience has been hex. You find that. I've put an example there of the binary number just in 1 byte there, that if you got to try and write those binary groups of binary numbers down, I'm sure you'll make a mistake.
Yeah, it's very easy to get lost very quickly.
You just got to do it one at a time and very slowly, where you can represent all that with just a group of 2 numbers, and of course decimal as well. Bandwidth. So what is bandwidth? Network bandwidth refers to the maximum amount of data that can be transmitted over the bus in a given time period, i.e. its capacity, typically measured in bits per second. I quite like the diagram below the image that we've got there, and thank you, Ben, for drawing that. If you think of the tube there that's passing data through, if we manage that data correctly, that tube is perfectly capable of handling that amount of data, no problem at all. In fact, it looks like we could pass far more through there and still get data through. What we don't want to do is overload that, because as soon as we reach capacity, we're going to start getting communication errors, data errors, and that's, in a safety critical system, that is not where we want to be. So a couple of points here. Bandwidth associated with the following, let me read that again. Bandwidths associated with the following networks. So these are the speeds that we're likely to see of what we'll discuss as we go through these series of videos. So we got LIN at 20 kilobit per second, so 20,000 bits per second. Classic CAN, which is your standard CAN for want of a better description, maximum 1 mega, so 1 million bits per second. A lot of data. Then we get to the likes of FlexRay, which is 10 million bits per second, which is kind of mind-blowing. And then 10 base T1S, this automotive Ethernet, again 10 megabits per second. So you might ask yourself, well, we've got one network already, why do we need another one at the same speed? Great question, which we'll answer later on.
Yeah, the thing to say here, these are all agreed in the protocol. So when the manufacturers of all the different systems agree the languages, once again we said, it's amazing how many different ways you can transmit a 1 and a 0.
Manipulate them almost, yeah.
Yeah, one of the ways you can change the protocol on a network and identify a network is by the speed of data transmission.
Did you notice what I did there? I asked myself a question and then I said it was a great question, which is quite good. I should stop doing that. What is baud rate? Baud rate comes up, and we need to know this when we use the decoder. So baud rate is a measure of the total number of signal transitions from high to low on the bus in a single second. So using PicoScope to measure the time span of a single transition, 1 bit, reveals the baud rate. Let's break that down into what that actually means. If we look at a pulse train of signals, voltages high and low, if we choose the smallest bit, the smallest pulse, and measure the width of that, we place that value, whatever that width is, over 1 over, so in this case we've measured the smallest bit here using PicoScope at 52 microseconds. So 1 over 52 microseconds, which is 0.0000052, gives us a frequency of 19.2 kilohertz. So in other words, 19.2 kilobit per second. Now you don't have to worry about the maths there, because if you look in the ruler legend, let me see if this point, yeah, if we look here, that when we measure this value, you'll see the actual frequency value comes up 19.2. So you don't have to do the calculation, but knowing that will help you identify the speed of the network you're on. And perhaps if you've got multiple twisted pairs, are you on the right twisted pair? You could be on a low speed CAN when you're actually trying to diagnose, say, powertrain CAN.
And this is another example of where understanding a little bit of the jargon helps. Because there's an awful lot of B's there, isn't there? Because you've got bytes, bits, bauds and bandwidth.
There's got to be another one that I just can't think of right now, but yeah.
So as much as this is possibly new to some of you, but revision for others, you understanding what a bit is, and that is the smallest single piece of data transmitted, is where you need to measure. That's a bit, and then we know how many how many bits can be transmitted per second is derived from the frequency, which is done for you in
the scope.
In the scope.
Yeah. All right, so let's summarise just quickly. Translating the scientific descriptions will help with interpretation. And you said, Andy, and I was a bit dismissive of the termination of the descriptions, but they're necessary.
They're absolutely necessary, because you've got to understand, if someone asks you something, and you need to understand specifically what that something is, and the easiest way to do that is to actually use the terminology associated around the networks. So we'll try and demystify some of these, but they'll be in the notes that come with the the video.
Yeah, and you'll see these terms pop up when we put what we call the further guidance to network, almost, because we'll touch on each network. We'll try and give you the fundamentals, but when you want to start breaking down packets and things like this and what they actually mean, these terms will pop up. So here I have node, of course, for computer. Transmission media, you might hear the term, what's the signal like on the media? What does that mean? Well, that is the wiring joining the ECUs. Network, a group of ECUs linked by cables, or not necessarily cables, over the air.
Yeah, it could be over the air. Bluetooth.
Impedance, a data bus cable resistance designed to ensure signal integrity and minimise errors. Topology, the physical configuration of each network. Gateway, that's that translator. I like that actually, it just works, doesn't it? It's one word explains that. The protocol, the rules that govern the language. So if that was language, that would be spelling, punctuation, spacing, terminology. Multiplexing, how we combine multiple messages into a single message. Differential bus, a twisted pair of wires where the voltage differential between the wires conveys the data, so not reference to ground. Communication, or the exchange of data and therefore information between ECUs. Encoding is the process of converting values into secure data for transmission and storage. Digitizing, I thought that kind of, you take an analog value and digitize it, encode it. Decoding is the process, the opposite of reconverting that encoded data into the original signal, and we will do some decoding. We will actually get some raw data and convert that into something that we all recognize. The transceiver, device used to drive the bus voltage high or low, or relay messages back to the computer. Remember, it's listening as well. The physical layer, I don't know whether we actually mentioned this in terminology, but this is the collective description of both the physical data bus and the raw signaling. You might hear this term, the physical layer. Is the physical layer damaged? What we're talking about is the data, the actual physical transmission media that conveys that data. Is it intact? Think of A minus B on a CAN network. That is the physical layer. Bits, nibbles and bytes represents groups of binary data, the compulsory language processed by the computer. So whilst we may not like it, we've got to know it. It's part and parcel of everything we're going to work with. A binary and hex formats used for representing computer data in either complex or compact form. The Pico decoder, that's within PicoScope 7 software and the hardware. That's how we capture and convert voltage levels into binary or hex values. Bandwidth, the amount of data that can be transmitted over the bus in a given time period. And then baud rate, which kind of links the total number of signal transitions on the bus in a single second. That's where we measure the smallest bit. I think that, have we got everything there? Network terminology, maybe there's something, there's got to be something. But
there are many terminologies that we haven't covered there, Steve, but they are, if you like, the building blocks of starting to...
Fundamental.
Yeah, absolutely, the fundamentals of the terminology used when we're talking about networks. Yeah. And there's probably enough there that someone could have a conversation with another technician, and if both of them understood networks, if they were using these terminologies, you would know people were talking about, and you could go to a vehicle with that level of terminology and get a long way.
I think so. I think so. And thanks for bringing it up, because, like I said, you reined it in right at the beginning, didn't you? And let's go right through terminology before we start diving into networks and such. So that brings us to a close for video 1. Thank you for watching, and we'll now move on to measurement techniques in video 2.